Hello, this is Dr. Schleith, and in this video I'll be going over the slides related to the learning outcomes belonging to the big idea in physics, dynamics, where we start to introduce forces into this study of motion that we've previously been thinking about kinematically. So remember, kinematics, that's the study of motion without regard to what's causing said motion. Forces are what cause said motion, and the study of forces is captured within dynamics. A lot of times we're going to start with Newton's laws talking about dynamics, and so this is no exception. Remember to keep a record of all of your work in a physics journal and send me photographs of your journal pages to my email by noon Friday each week. All right, so I'll kind of go through each learning outcome as we progress through the slides rather than giving you all the learning outcomes up front. The first learning outcome is to be able to just state Newton's laws of motion. We're going to revisit Newton's laws of motion in a subsequent chapter when we take a look at momentum specifically, but we'll sort of just introduce those laws now as a way to move forward. The first law can be thought of as an object will remain at rest or in a state of uniform motion unless it is acted on by an external force. You've probably heard some variation of that statement throughout your academic career. I like to think of the first law as objects won't just accelerate on their own. They're going to keep on moving how they're moving at a constant velocity. It could be zero, right? So at rest. So something's going to have to make it accelerate. And that kind of sets us up for the second law, which says, one way to think about that would be F equals ma, force equals mass times acceleration. So it reads on the page here, for a body of constant mass. And so that's a sort of a special case. We're talking about something with constant mass. Newton's second law becomes F equals ma. Like I said, when we study this through the lens of momentum, we'll see that the definition of force is the rate of change of momentum. And momentum being defined as the product of mass and velocity, it could be either the mass or the velocity that's changing, or both, for a force to be applied on an object. Kind of think about that like with rocket science. A rocket is a continuously variable mass. It's expending its fuel, and so it doesn't have constant mass. And so we can apply sort of a more general application of the force laws when we think about it through the lens of, force is the rate of change of momentum. But for a body of constant mass, the acceleration is directly proportional to the resultant force applied to it. The resultant force F, mass m, and acceleration a are related by the equation F equals ma. And that equation is incredibly important for students of physics. Oftentimes, where you're going to begin most of your calculations. Arguably the most important equation when you first start learning physics, or in all of physics, F equals ma. And don't forget about adding up the force vectors on the left side of that. It is the net force. And so we spent a lot of time learning about ways to represent quantities that are vectors and how we add those vectors. And so force is a vector. And so keep in mind how we add vectors. That will sort of sum the left side of the equation, give us the resultant force, which will then be directly related to the acceleration of an object. Again, captured by the equation F equals ma. The third of Newton's laws of motion says, when two bodies interact, the forces they exert on each other are equal in magnitude and opposite in direction. So forces exist in pairs, equal in magnitude, opposite in direction. Forces, Newton's third law of force pairs, are always acting on two different objects. So when we're drawing a free body diagram, we're typically considering the forces that are acting on a single object. Remember, though, that a Newton's third law force pair is between two different objects. Oftentimes, we can consider equal and opposite forces that are acting on a single object, and that doesn't mean that they're a Newton's third law force pair. Just because they're equal and opposite doesn't automatically make them a Newton's third law force pair. For that, we have to be looking for forces that are of the same type. For example, the weight force, the force due to gravity, which is weight, that's really the influence of Earth's gravitational field on our mass here, sort of the force that you're feeling right now. There's an equal and opposite force of your mass pulling up on the Earth just a little bit. So the forces there are the same, but it is the wildly different mass between you and the Earth that means the acceleration of each object is going to be a lot different. For example, when you push down on the Earth and you jump up into the air, you're really pushing the Earth down underneath you. And if you think about the Earth as a rigid sphere, then it's accelerating, a negligible amount underneath your feet while it accelerates you up a lot more. So the forces are the same there, but the mass is different, and therefore the accelerations are going to be different. Again, that's all captured within Newton's second law of motion. So all of Newton's laws, rather, are related to each other, and that's why if you think about the first law as, objects aren't just going to accelerate on their own, they're not just going to change their velocity on their own. And remember, changing a direction is also an example of acceleration because velocity is a vector. So objects aren't just going to change their direction or change their velocity on their own. We're looking for forces, net forces, to cause those changes in velocity, those accelerations. And so force equals mass times acceleration, and those forces exist in pairs, equal in magnitude and opposite in direction. That's a quick summary of Newton's three laws of motion. Another learning outcome is to be able to identify the forces acting on a body in different situations. This takes a lot of practice working with different problems, becoming familiar with each of the different forces. And there are typically equations where we can sort of describe the forces in terms of equations that we've deduced. So, for example, friction is a type of force. The force of friction is equal to the coefficient of friction times the normal force. And so the normal force is another type of force that we need to be able to identify. The normal force is a force that acts normally or perpendicular to a surface. And so really, when we think about the force due to gravity, the weight force that I mentioned earlier, that's the force of Earth pulling down on your mass. But what you really feel is the normal force of whatever object that you're seated on sort of pushing back up on you. For example, if that seat weren't there, then you would accelerate down towards, sort of the direction that the force due to gravity, the weight force, wants you to go, which is always down. And so there's always an object here near the surface of the Earth that's exerting a normal force back up on us, and that's really sort of what we feel as our weight. It's the normal force, which is really a result of the electrostatic repulsion of sort of the electrons and the atoms of the solid object that you're seated on, and yourself sort of repelling each other, sort of those electrons. There's an electrostatic repulsion. That's sort of what we feel as the normal force. One of the overarching goals in science is to come up with a grand unification theory, a grand unified theory that really describes how all of the fundamental forces are related. And so when we talk about types of forces, we'd be remiss if we didn't really think about the fundamental forces, that scientists have really deduced that there are four fundamental forces, and they are gravity, the weak nuclear force, the strong nuclear force, and electromagnetism. And a lot of the work in physics that is much celebrated is when we unify some of those fundamental forces. For example, in 1979, Abdus Salam unified electromagnetism and the weak nuclear force, sort of an electroweak theory. So sort of like the holy grail of physics is to come up with a grand unification theory, a theory that would unify sort of all of the forces there. And that's incredibly tough to do. There are, some would say many grand unified theories, but they're really hard to test. So whenever we're thinking about types of forces here, sort of physics 101, high school physics, we can always think about, well, what's the fundamental force? We already mentioned, the force due to gravity or weight. So gravity is a fundamental force. But when we think about like the normal force, it's really an electromagnetic force. It's the electrostatic repulsion, remember, of the electrons and the atoms of the solid objects that are sort of repelling each other, sort of what you feel is that contact force. The applied force, like you see here in the figure, somebody pushing on a cart. And so that's, again, an electrostatic repulsion between sort of the electrons and the atoms of the two solid objects, the person's hand and the cart there, right? So two objects, we sort of think about with the same force that the person pushes on the cart pushes back on the person. That's an example of Newton's third law force pair between two different objects, equal in magnitude but opposite in direction. The drag force is a force that we'll consider with specific problems. Drag is proportional to velocity. And so as an object crashes through a medium, a fluid like air or water, those particles are going to sort of push back against the object that's crashing through them, and that force is drag. Here it's represented by somebody in a parachute, and so there'd be a drag force with all of the air particles that are being sort of caught by the parachute. But even before the parachute was deployed, a skydiver, like we see in sort of the second picture here, who is falling as a result of their force due to gravity, their weight, would crash into enough particles that the force would actually eventually equal the weight. And at that point, there would be no net force. The skydiver will still continue to fall, but they're no longer going to accelerate. And so that would be an example of reaching terminal velocity, where a skydiver is going to speed up or accelerate as a result of their weight, but there's going to eventually build up enough drag force that will equal the weight, and no longer will the skydiver continue to accelerate towards the ground, but continue to move to the ground at constant velocity until hopefully a parachute is deployed there, which will create a net force upwards and decelerate the skydiver to a safer sort of landing speed there. But eventually, because the drag force is proportional to the velocity, once that drag force once the parachute is initially deployed, I should say, there's a much stronger drag force, but as the velocity decreases, once again, the drag force will again equal sort of the weight acting downward, but just at a much safer landing speed. And so we'll look at all of those changes in motion of a parachutist throughout a successful skydive. Springs have forces, and we'll study, the force in a spring. Magnetic forces, tension forces like in a rope, buoyant forces. The buoyant force is, again, the result of sort of thinking about atoms crashing into objects. And so a hot air balloon, there's, air particles that are sort of creating a force upwards on the balloon, and that creates a net force up. And so lift. Lift is another type of force, kind of think about similar to the buoyant force. Here's an example problem where we'll kind of look at Newton's second law, the definition of acceleration, to solve this. It says when a golfer hits a ball, his club is in contact with the ball for about 0.0005 seconds, and the ball leaves the club with a speed of 70 meters per second. The mass of the ball is 46 grams. A, determine the mean accelerating force, and B, what mass resting on the ball would exert the same force as an A. And it asks us to solve with Newton's second and the definition of acceleration. So let me grab a writing tool here, and we'll just do our working. Remember that Newton's second law tells us that force equals mass times acceleration. Got my equal sign there mixed in with my F. So force equals mass times acceleration. We're given the mass, but it's important that if we're going to report a force in the SI units, which are newtons of force, then that is defined as a kilogram meter per second squared. And so we need to convert 46 grams into kilograms. There are 1,000 grams in a kilogram, and so 46 divided by 1,000 gives us 0.046 kilograms. So we can just substitute that value in for the mass here, solving for the force in newtons. Being mindful of the units is something that a careful student of physics is going to get really good at, knowing the definitions of the derived units, which is a subsequent learning outcome that we'll address later on in the slides. But here's an example of it now. A newton is defined again as a kilogram meter per second squared. So acceleration is going to need to be calculated from the information given. A golfer hits a ball, his club is in contact with it for a certain amount of time, and the ball leaves the club with a speed of 70 meters per second. Remember that acceleration, which they actually instruct us to use the definition of acceleration in our working here is defined as the rate of change of velocity. And so acceleration is the final velocity, v, minus the initial velocity, u, divided by the time to move from u to v, v minus u over t. The initial velocity, it can be understood in this problem as 0 because the ball is just sort of resting there on the tee. It leaves at a final velocity of 70 meters per second. And so the change in velocity is 70 meters per second. Final velocity minus 0, or just 70, but for completion's sake, I'll write out the working. Now it's in contact for 0.0005 seconds. I'll put an S here for seconds, and not to be confused with the 5 here, right? 0.005 seconds. The units here in the numerator are meters per second. So once again, being very careful with the units, we see that we've got on the right side of this equation, kilogram meter per second, or kilogram meter per second squared. Let's take a moment to calculate. divided by 0.0005 gives 140,000 times the mass, 0.046, to give 6,440 newtons of force. That's a 6 there. I think the mouse kind of got away from me a little bit. 6,440 newtons. Let me clean that up. What's better than cleaning up sort of the tidiness of your writing is cleaning up the significance of your digits. And so always check, can we report our final answer to this level of significance? I'd feel a little bit better with maybe 6,400 newtons or 6.4 by 10 to the 3 newtons. Get comfortable with reporting values in scientific notation as well. What mass resting on the ball would exert the same force as in A? So if we were to sort of set a mass on top of the ball, what mass would it take to give us that much force? This is really a problem about weight, sort of the force due to gravity. So it's saying, how massive would something need to be so that the weight force that it exerted as it sort of rested on this thing would equal the force that you could deliver to it, with a golf club. So 6,440 newtons. We want that to be the weight. Now, weight is equal to the mass of the object times local g, the strength of Earth's gravity field. And it really is just a restatement of Newton's second law, F equals ma. The force is just weight, mass is mass, and then the acceleration is the acceleration due to gravity. And another way to think about that is how many newtons per kilogram, newtons of force per kilogram of mass acting on the object in the gravity field. So if we multiply, we're solving for the mass here, so saying what mass resting on the ball would exert the same force. And so let's make mass the subject of this equation down here. So m would equal the weight, which we want the weight to be the same force that we delivered with a golf club. So the 6,440 newtons, we're going to substitute it for weight. And then the value of g here on the surface of the Earth, 9.81. And the units that are equivalent to meters per second squared, the acceleration due to gravity, are newtons per kilogram. In other words, a newton per kilogram is equivalent to a meter per second squared. And you could see that if you substituted in the base units for the derived unit newton into that. Remember that a newton is a kilogram meter per second squared. So a newton per kilogram, the kilograms would cancel and you'd still have meters per second squared. Another way to think about the units of g. Let me remind myself that I'm putting the units here in parentheses. Remember that the weight force is also going to be in newtons, and so newtons is going to cancel out, and we're going to be left in units of kilograms. All right. So 6,440 divided by 9.81 newtons per kilogram gives us 656 kilograms would be the mass that you would need to equal that much force. Which we could round up to 660. That's a lot of kilograms. The slide goes on to say, solve with impulse momentum theorem. Impulse is just the quantity force times time, and it's equal to the change in momentum. We'll revisit this type of working once we've had a chance to study momentum in a little bit more detail. But as I mentioned earlier, force is the rate of change of momentum. And so that's really just reorganizing that definition where the change in momentum over the change in time would give you force. Multiplying both sides of that sort of definition of force by the change in time gives us this impulse momentum theorem that just says the impulse delivered to an object, the force times the time that that force is delivered, will equal the change in momentum of that object. So that's just something to look forward to as we continue to study this later on in the year. Let me go ahead and clear this working. I leave it to you if you'd like to work through that based on your knowledge of momentum currently, especially for those students that have went through pre-AICE already, and then describe both equations and solutions. And are they saying the same thing? Think about that. Another learning outcome is to be able to describe how the motion of a body is affected by the forces acting on it. This is incredibly important because one of the powerful things about physics is its ability to predict. And so with dynamics, when we can start to understand how the forces acting on an object will affect its motion, we can predict, where that object's going to move to, what forces are needed in order to accelerate an object to sort of get it to where we want to go. So there's some good notes here on this slide related to this learning outcome. I'm going to go ahead and read them through for completion's sake. It says the acceleration produced by a force is in the same direction as the force. That's really thinking about Newton's second law in terms of that acceleration is a vector and force is a vector, and those vectors are going to point in the same direction. The direction of the net force is the direction the object accelerates. When there are two or more forces, we must determine the resultant force. This is what I was talking about earlier about adding up sort of the left side of that equation, getting the net force of the resultant force. This is accomplished by identifying all forces using a free body diagram. Force vectors not acting along the assigned x and y axes must be resolved so the magnitude and direction of the resultant force can be determined. One convention is the sum of the forces in the y direction equals mass times the acceleration in the y direction, and the sum of the forces in the x direction equals mass times the acceleration in the x direction. Sum of the force in the x direction equals mass times the acceleration in the x, and then also for the y direction. The two components are added together later, right? So figure out all the forces in the x, figure out all the forces in the y, add them back up, and then you can create a final vector determined by Pythagoras' theorem, right? So construct sort of legs of a right triangle, and the net force would be the hypotenuse, as determined by Pythagoras' theorem. One of the learning outcomes is to solve problems using F equals ma. Remember that force is measured in newtons, the SI unit, mass in kilograms, and acceleration in meters per second squared. We'll see this a lot. Here's an example. It says the mass of a spacecraft is 70 kilograms. As the spacecraft takes off from the moon, the upwards force on the spacecraft caused by the engines is 500 newtons. I think there should be sort of caused by the engines is 500 newtons. The gravitational field strength on the moon is 1.6 newtons per kilogram, right? Sort of another way to think about the acceleration due to gravity or the strength of the gravity field in newtons per kilogram. It wants us to determine A, the weight of the spacecraft on the moon, and B, the resultant force on the spacecraft, and finally C, the acceleration on the spacecraft. All right, let's go ahead and grab a writing tool and work through this. The weight of the spacecraft on the moon. The equation for weight, remember, is that weight is equal to mass times local g. They tell us that the spacecraft has a mass of 70 kilograms, so we can substitute that in for mass here. Kind of nice when we don't need to sort of do any conversions. We just recognize that we're in the correct units. And it gives us local G on the moon, 1.6 newtons per kilogram. So 1.6 newtons per kilogram. And we can see already with the units that when we multiply these two, kilograms will cancel, and we'll be left with newtons of force, which is force due to gravity or weight. So 70 times 1.6 to give us 112 newtons. That would be the answer to A. Cleaning it up for significant digits, we could report the answer to two significant digits, say 110 newtons. I leave it to you to take that note down in your journal. A better answer here might be 110 newtons. The resultant force on the spacecraft. As the spacecraft takes off from the moon, the upwards force on the spacecraft caused by the engines is 500 newtons. So if we want the resultant force, so we're only sort of considering those two forces, in the sort of vertical direction. So we get an upwards force of 500 newtons. Thinking about the types of forces learning outcome from previously in the slides, that certainly wasn't a complete list of all the different types of forces, and so we'll spend a lot of time sort of identifying different forces. The name of this force, sort of like in a spaceship, is called thrust. So this upward force here, 500 newtons, thrust delivered from the engines. And weight acts in the downward direction, and we already calculated the weight of the spacecraft to be 112. I did not draw those vectors to scale. The important thing is the direction there. We can just sort of calculate the magnitude here. So the resultant force is going to be the difference between them because those vectors oppose each other. The 500 newtons acting up and 112 newtons of weight acting down yield a net force of 388 newtons up. Up. 388 newtons up, or about 390 newtons up, again dealing with significance. The acceleration of the spacecraft. In order to calculate the acceleration, we're going to rely on Newton's second law, F equals ma. If F equals m times a, then a would be equal to force divided by mass, right? Sort of just dividing each side of that equation by m. Because we want to solve for the acceleration, we can make that the subject of our equation here. Remember that Newton's second law really says that the net force is equal to mass times acceleration. And so one calculation leads to the next here. We've calculated the resultant, or the net force, in part B, 388 newtons. And so that net force acting upward, I think my writing tool has gone haywire there. I can undo that. 388 newtons of net force upwards over the mass of 70 kilograms. Sort of the unrealistic thing about this question, I suppose, is that usually the mass of a spacecraft is going to change because all of its fuel is being sort of expelled there. But this question is a little bit simpler than that. I would say somehow this spacecraft has a constant mass of 70 kilograms. To make it a little bit easier for us to deal with. So 388 newtons divided by the constant 70 kilograms, the somehow constant 70 kilogram mass of our rocket there, would be 5.5 meters per second squared of acceleration. The purpose of this question is really practice with the learning outcome, solve problems using F equals ma, also reminding ourselves about how to sort of add vectors that act in different directions. And of course, the force due to gravity being weight and how that sort of resembles Newton's second law. Let me now cite and sort of give credit to the text endorsed by Cambridge for, this is AICE Physics course here. If you want to acknowledge the authors of this text here. Jones, Chowda, and Woodside, Cambridge University Press, for the source of these questions. Moving on. And of course, all of the learning outcomes also, come from that text. Relate derived units to base units. There are 7 base units in science, sort of the agreed upon base units, and everything else, every other unit in science is derived from those 7 base units. And so this is a complete list, and some of these are beyond the scope of AICE Physics. For example, we don't really study luminous intensity in candelas, and I think even when we do study luminous intensity, the candela is not often used as a base unit, but rather the derived unit for power, for luminous intensity, the watt. And so we can see down here on the list, the watt, the derived unit for power. That's another way to sort of measure luminous intensity. Brightness. So the length, the base quantity length, is measured in meters, mass in kilograms, time in seconds, electric current in amps, temperature in degrees Kelvin, the amount of substance in moles, and luminous intensity, as we mentioned, in candelas. Each of those is the subject of this course, with the exception of luminous intensity candelas. Moles is reserved for A-level physics. It's really important to know all of the SI prefixes, the symbol that sort of represents them, and the order of 10 that they represent. It makes it a lot easier to do conversions and calculations when you can substitute in a factor of 10, say 10 to the 3, when you see the word kilo, which you typically want to do, except for in the case of kilogram, because remember, the kilogram is sort of that one SI unit that has a metric prefix in terms of the base unit, right? It's not like the kilometer, the kilometer is the base unit of length, it's the meter. And so that's important to keep in mind, that a Newton, the derived unit, is defined as a kilogram meter per second squared. So we typically do want to leave mass in kilograms or convert it into kilograms. It'd be really important for students to get these notes down in your journal. All of the factors of 10, the corresponding name in the metric system, the symbol, and if you got the order of 10, I don't know if you need to have it written out in standard form. This is certainly not a complete list of derived units here, but these are some of the important ones that we'll study throughout the year. You could maybe dedicate a page or a couple of pages in your journal, one to the SI base units, and that is a complete list. Those, like the kilogram was redefined a few years ago, and so it is perhaps true that in the future they might redefine, like remove amps as a base unit and maybe make the coulomb so as the unit of charge sort of the base unit, rather than a unit for electric current. But those are sorts of decisions that are made by groups of scientists that sort of get together and agree upon, well, this makes sense to redefine it this way. So the definition, for example, of the meter has changed over the years, and we've got a pretty good definition of the meter right now. I believe the original definition of the meter was the distance from the North Pole to the equator divided by 10 million. And the idea was to sort of create a definition that would be reproducible, that somebody, if they really wanted to, could travel from the North Pole to the equator divided by 10 million and sort of get that standard length. We now define the meter as the distance that light can travel in a vacuum in a certain fraction of a second, because we know the speed of light so accurately. Let me take a moment to talk about that. So the meter right now is defined as the distance that light can travel in 1,292,792,458 of a second. Because the speed of light is that many meters per second, right? So that's sort of value right there, 299,792,458 meters per second. That's the very precisely known speed of light. So if we know that the speed of light travels exactly that fast in a vacuum, that many meters in 1 second in a vacuum, then we can define the unit of length, the meter, as the distance that light travels in 299,792,458 of a second, right? It will have went exactly 1 meter in that fraction of a second. And so that's the current definition of the meter. There are very precise definitions for, each of the base units, just so that there are, again, sort of reproducible ways. The kilogram, there's sort of an interesting, history of that, Lagrange K, and sort of the, until very recently, the kilogram was tied to a physical object. And so I leave it to you to research that history on your own. The work that we'll do with this learning outcome relating derived units to base units will be typically checking equations to make sure that there's what we say homogeneity, the sameness on each side of the equation. So we want to make sure that, as we saw earlier, that a Newton is equal to a kilogram meter per second squared, that those are really the same thing. So if we see, sometimes we can determine what the units of sort of an unknown quantity are by looking at sort of a known equation. We can sort of have what we say a sanity check on our working and make sure that the units at least agree on both sides. By checking and making sure that the units agree on two sides of an equation, we don't guarantee that the equation is valid, but we can quickly disprove the equation invalid if we do find that there's a mistake with the units. In other words, the units have to agree on both sides of the equation. And so keep that in mind, that that's typically the work that we'll do. We'll sort of look at equations and make sure that we've got the same units on both sides, or we'll be able to sort of puzzle together and figure out what the missing units are sort of in one term or another, because we'll be expected to know everything else in the equation. That's typically what we'll do with this learning objective. And sometimes we do have to convert, with these metric prefixes. We study things that are, really big numbers and really small numbers in physics. Here's an example where we're sort of looking at how forces are affecting the motion of an object. It says a metal ball is dropped into a tall cylinder of oil. The ball initially accelerates, but soon reaches a terminal velocity. To kind of mention terminal velocity, something falling through a sort of a viscous liquid, like a skydiver falling through the air, will eventually have enough drag force that it will equal the weight. The same sort of physics applies here. It's just sort of a metal ball in place of a skydiver and oil, in place of air. By considering the forces on the metal ball bearing, explain why it first accelerates but then reaches terminal velocity. Describe how you would show that the metal ball reaches terminal velocity. And there, in these bullet points, it really sort of addresses that question. It says the force of gravity causes acceleration. When the ball encounters the oil, it experiences a resistive force proportional to the velocity of the ball. When the resistive force equals the force due to gravity, the ball will no longer will accelerating and has reached terminal velocity. Well, that's sort of poorly worded there, certainly in a typographical error. It should read, the ball will no longer be accelerating and has reached terminal velocity. So this word will should say, be. The ball will no longer be accelerating and has reached terminal velocity. And then to address part B here, it says, by plotting the ball velocity as a function of time, or measuring the ball velocity as a function of time, and then plotting the data, one would notice the slope of the line equals the ball's acceleration. The slope of the line, which is equal to the ball's acceleration, would change its slope to 0 at the point the ball reached terminal velocity, right? And so we'd see sort of a constant velocity once it had reached that final speed, and that would be evidenced on a velocity time plot of a line that didn't have a slope of 0. And that would be one way to show that it had indeed reached terminal velocity, by collecting the data and then putting it on a plot. Think about how the same explanation in the first bullet point here, once it's corrected for the typographical error, would also apply to the skydiver falling through air, right? So it's the sort of same basic physics that we can understand there that just applies to different objects, in different media, but the same forces in the way that they affect the motion of the object is the same. Here are a few example problems connected back to that first sort of definition of speed, where speed is distance divided by time, and they give us distances and times in different SI units with different metric prefixes, and so it really is going back to those orders of 10 and being careful to sort of see what the final answer would be. And so we typically want speed in meters per second. Let's say we needed to know a change in speed so that we could plug it into the equation for momentum, mass times velocity. We would want the velocity in meters per second, because if we go on to consider, say, how an object changed its speed, how it accelerated, then we'd probably want those in meters per second squared. So if we wanted to consider the forces, as we do in dynamics, and measure that in newtons, we know that a newton is a kilogram meter per second squared. So if we measured something in the lab that went 3 micrometers in 5 milliseconds, we could convert that into meters per second, because we might want it in meters per second to do something further with it. Maybe consider the forces that were acting on something that made it move 3 micrometers in 5 milliseconds. And so we'll just sort of plug each one of these distance and time data points into the equation for speed and do the conversions, and I'll show you sort of a way to do that. So we have speed, which is equal to distance divided by time, and so each one of these A, B, and C give us a distance, so and a time. 3 micrometers of distance divided by 5 milliseconds of time. If you consult your notes, you'd be able to find that micro, that prefix, stands for millionth, 10 to the negative 6. So we can simply substitute that order of 10 for the prefix micro and think about 3 micrometers is 3 by 10 to the negative 6 meters, divided by 5 milliseconds. So 5 in milli is represented by the order of 10, 10 to the negative 3. 10 to the negative 3 is the same thing as milli. And so by knowing the order of 10 that each one of the metric prefixes sort of stands for, we can plug that in our calculator and make short work of the conversion. So my calculator can type in 3 times 10 to the negative 6 divided by, and be sure to open parentheses if you're sort of typing it in the way that it looks there, 5 times 10 to the negative 3. We want to divide by that entire quantity, not divide by 5 and then multiply by 10 to the negative 3. 0.0006. Remember, we've talked about this. It's a good habit to get into, to always, when you're dividing by values in scientific notation, to use grouping symbols. So we have 6 by 10 to the negative 4. Meters per second. 0.0006 meters per second. We can use the same sort of structure for the conversions in B and C here, just sort of different numbers with different metric prefixes. And so now we have 6, and then kilo is 10 to the 3. So you have 6, 10 to the 3 kilometers over 3 megaseconds. So a capital M here is a megasecond. So this is part B right here. 6 kilometers divided by 3 mega is a million, so 10 to the 6 seconds. Again, we just type that into our calculator. Or you can get comfortable with just sort of, working with the exponents here. As you sit for the exam, it's both important to be efficient in your working, and so when you're very sort of comfortable with how this sort of just works out, with the rules of sort of subtracting these exponents, for example, when we're dividing, then that might be sort of the better way to go. But if you're using your calculator anyway and you're sort of worried, well, what if I make a mistake here, then it's a good way to sort of check yourself, especially as you're practicing, to do the working just on paper and then to check yourself in the calculator. So the answer that you should get would be 2 by 10 to the negative 3. And if we think about how that would work here, 6 divided by 3 is 2. And the rule again for how we treat these exponents here when we're dividing is to subtract the exponents. And so 3 minus 6 is negative 3. And so we get 6 divided by 3 is 2. And then the order of 10 would be by 10 to the negative 3 because we're subtracting them. So if you remember that, it is perhaps faster to just sort of go straight to this answer rather than typing that in the calculator. But it's really good to sort of practice with that to build your confidence that you are doing it correctly as you're working with the material, especially when you're first learning it. The final one here, hopefully by now you've had a chance to maybe pause the video, go into your notes. You know what a picometer is, you know what a nanosecond is. And so if you haven't already tried your hand at this calculation, pause the video now and go through the working for yourself, and then hit play again and we'll compare notes. So a picometer is 10 to the negative 12 meters. So we have 8 picometers divided by 4. And then nano is a billionth, so 10 to the negative 9. And our units will be in meters per second. So here, that's a 9 down there. 10 to the negative 9 is the order of 10. I think that got a little bit messy there. So 8 divided by 4 would be 2. And negative 12 minus negative 9, what's that? We're taking away a negative, and so we're really adding it back. Negative 12 minus negative 9 is negative 3, right? So we'd have 2 by 10 to the negative 3 meters per second. Or you could show it like I did up here, meters per second with the negative index. 8 times 10 raised to the negative 12 divided by 4 by 10 to the negative 9 is 2 by 10 to the negative 3. So once again, it builds your confidence when you see that in the calculator. Note that we got the same velocity in both B and C. And so something that travels 6 kilometers, a long distance, in 3 megaseconds, sort of a long time, ended up being the same velocity as something that went 8 picometers, which is a really tiny distance, in only 4 nanoseconds, a short amount of time. And so something that goes, a long distance in a long amount of time, or a short distance in a short amount of time, ended up being the same when we sort of put them in the same units, meters per second. And that just sort of highlights why we want to kind of think about things with standard units. That concludes the end of these slides, but be on the lookout for future videos. We're going to cover each one of the learning outcomes in more detail.